Okay, everyone, let's do this question on electromagnetic waves and the diffraction, refraction, and reflection of waves in this past paper here. This is from January 2023. This is a CSEC physics paper, right? So this is question 4 on that paper, and it's asking us to name the electromagnetic waves in each of the regions labeled A, B, and C in this version of the electromagnetic spectrum that they've shown here in this figure, right? So first, let's look at A. We see that A, right, would be the region that's directly below infrared region, and we know that that's where microwaves are, right? So that's the microwave region. So we put microwave for A. And next we have our infrared, then we have visible light, and we know that above visible light, right, at a higher frequency, we're gonna have ultraviolet light. So we know that B should be ultraviolet light, and then we have X-rays, and then the only thing that's more higher in frequency, right, and shorter wavelength than X-rays would be the gamma rays. So we know that C is supposed to be our gamma rays, right? So that's all for 3 marks. We're good and we're moving along. Okay, so B is saying figure 6 represents some wavefronts, right? Some wavefronts approaching a barrier with a narrow gap, which is smaller than the wavelength of the wave, right? And there are, so this is our figure. So we have these wavefronts, and these wavefronts are approaching this barrier, which has a narrow gap here. And that narrow gap is much smaller than the wavelength of this wave, right? So they're saying that on figure 6, they want us to draw 3 wavefronts. So only 3 wavefronts after they have passed through the narrow gap, right? So if you have this wavefront that's approaching this narrow gap, and the wavelength of this, right, is larger than the gap itself, what you will see is very large diffraction patterns taking place, right? So that wave is gonna spread out as it passes through this gap. And so this would be our first wavefront, this would be our second wavefront, and our third wavefront. So we've shown the 3 wavefronts here after these wavefronts pass through this narrow gap. So diffraction will take place, right? And remember that when you look at the wavelength of the wavefront in comparison to the gap, right? The width of the gap, that will determine the extent to which it is diffracted, right? Because this is a small gap, we see that there's like a large diffraction taking place here. And so those waves just spread out, and we're showing 3 of them, okay, as the question asked. And so that's for 2 marks. So we're good and we're moving along. So next, they're asking us to define the term refractive index of glass, right? So of a very specific medium of glass. So here we can define the refractive index of glass as the ratio of the sine of the angle of incidence, right, to the sine of the angle of refraction when light rays travel from a lesser dense medium to glass, right? So that should suffice. We've included that the rays are traveling from another medium to glass, right? And so that's what our ratio would be, right? So that if I were to write out that in more detail, or from a formula standpoint, it would be that the refractive index of glass is then equal to the sine of the angle of incidence, right, divided by the sine of the angle of refraction when light rays travel from a lesser dense medium to glass. So the refractive index of the lesser dense medium would technically be under here, right? So say it's coming from air, it would be like this. So the ratio of the sine of the angle of incidence to the sine of the angle of refraction is what we call the refractive index of glass in this particular case, right? So that's what that would look like from a formula standpoint, and this is all of that in words, right? So for 3 marks, we should be good here. Okay, so let's move along now to see what else they're asking. So for part D, figure 7 is showing an array of red light. So let me scroll down a little bit so we can see it. So figure 7 shows an array of red light right? So this is our ray of red light coming in. It's incident on the face XY. So this is the XY face of the glass prism. So we have this red light coming in. It's incident on this face, the XY face, at this point S, right? So this is our point of incidence. So you notice that we have a normal that we can draw at that point of incidence. So we have this normal line, this dotted line here, right? Dashed line here, rather. And then they're telling us that the refractive index of glass for red light is 1.5. And we already defined what the refractive index is from up here, right? So we're set up from here. We're ready to go down here. Okay. So this is our incident ray on this face. This is our normal, and this is our refracted ray. Okay, so let's just stop at that part for now and see what they're asking us. They're saying that we should calculate the angle of refraction in the glass at S, right? So when the incident ray comes to this point of incidence, and then it gets refracted, what is the angle of refraction, right? And the angle of refraction is going to be the angle between the refracted ray and the normal. So it's this one right in here, right? This is our angle of refraction. And if we come back over here, this is our incident ray, and this is our normal, right? And we know that the angle of incidence is the angle between the incident ray and the normal. So this is our angle of incidence here. And we can calculate that because we know that this whole thing, right? This whole thing is supposed to be 90, right? And so if we know that this angle that they're showing us here between the XY face and the incident ray is 55, then we know that the remainder, right, which is our angle of incidence, is going to be 90 minus 55. So we get 35 for our angle of incidence, right? And so now to calculate the angle of refraction now, what we're going to do is use that definition, right, of the refractive index of glass, which is simply this formula, where it's N2 over N1 is equal to the sine of the angle of incidence over the sine of the angle of refraction, right? And we know that our second medium is glass because it's going from air to glass. So this is the refractive index of glass, and this is the refractive index of air, which we know is 1, right? So all we have to do is rearrange this formula, making our sine theta r the subject. So when we do that, we end up with sine theta r is equal to N1, right, times sine of theta I divided by N2, which is the refractive index of glass. And so, of course, if we want to find the theta r, which is the actual angle, we have to do the inverse sine of all of this, right? And so when all we have to do from this point now is just plug in our values here, right? Remember up here, we had calculated the angle of incidence. So what we're going to do is just plug that in here, right? Theta I, that's sine 35, and we know that N1 is 1. So there's an imaginary 1 here for the refractive index of air. And then underneath here was our refractive index of glass, which they told us is 1.5. So we just plug that in here. And then we're good from here. It's just a matter of plugging this into the calculator now. So we calculate this part, and then we find the sine inverse of this part, and we come out with a refractive angle of refraction of 22.3 degrees, right? So that's our answer there for 3 marks. So all we're doing is we're using this formula, right? Snell's law, or this definition of what a refractive index is. And then we're rearranging for what we want to find, which is our theta r, or angle of refraction, right? And we know what the angle of incidence is. We can calculate it from the figure, and that's what we did first. And then we were able to just plug in everything else because we knew what the refractive index of glass was. We know the refractive index of air, where the ray is coming from, is 1. And so all we had to do was rearrange for theta r, and that's what we did. And we ended up with 22.3 degrees, okay? All right, so moving right along to part 2 of that question, they're asking us to calculate the critical angle C for glass to air, right? So remember, when we talk about a critical angle, we're always talking about going from a more dense medium, right? So in this case, glass is our more dense medium, and we're going to a less dense medium now, which is air, right? And so that's when critical angles come into play, right? So let's go back and look at the figure to see what they're asking us to calculate. They're asking us to calculate the critical angle, but let's look at the figure and see what that is, right? All right. So just to go back from over here, we have our incident ray coming in from air, then it's going in, it's touching the surface, and it's getting refracted in the glass, right? And so once we're in the glass now, this ray is incident on this face, right? The YZ face, it's incident on it. And then what we see is that there's some kind of refraction again that's taking place as it's going from inside here. The ray is going from inside the glass now to the air, right? So what you see is that actually once it's incident on this YZ face, it doesn't end up leaving, right? The ray doesn't end up leaving the prism per se. What happens is that it kind of just grazes along this surface of this YZ face, right? It doesn't leave. What happens is that it bends so much, right, that it actually ends up coming back on the prism itself, right, instead of being somewhere out here. And that's because over here is a less dense medium, right? And we know that when we go from a more dense medium to a less dense one, the ray is gonna bend away from the normal. So that's what we see happening here. Now, this is a special case because it actually grazes along the surface, and the angle that's needed for that to happen, for the incident ray to just graze along the surface when it gets refracted, we call that angle the critical angle, right? And so what we're being asked to find then is this angle here, right? So the angle of incidence in this case is the same as the critical angle. So the theta I, which is what this is, because this is our incident ray in this case, is equal to our critical angle, right, in this case. So they're asking us to find what this is, right? And there's a very simple formula that we use to find critical angle, right? And so that formula is actually just that the sine of the critical angle, or the sine of theta C, however you write it, right? It's that the sine of the critical angle is equal to 1 over n, and the n is the medium that you're coming from. So in this case, we're coming from glass and we're going into air. So this refractive index is representative of that glass that we're coming from, right? The more dense medium. So this is our formula. Sine C is equal to 1 over the refractive index of glass. And so we can plug in the refractive index of glass here. That's 1.5. And then, of course, we have to do the inverse sine to come out with our actual angle, right? Which we ended up getting 41.8 degrees for that, right? So that's all that we have to do here, really. Just apply this formula for critical angle, but make sure that you know that the refractive index that's in that formula is for your more dense medium, okay? Which in this case is glass. And then we're good. So we got 41.8 for its critical angle, and that's 3 marks. We're good to go, right? So thirdly and finally, they're asking us to identify the critical angle in figure 7, right? So let's go back up. We had identified it before, and we said that it's this angle here, right? It's the angle that this incident ray that's incident at this point forms between the normal and the incident ray, right? So this is our incident ray, this is our normal. And so this angle here will be our critical angle, and it's the angle at which the refracted ray is just grazing along the surface of that prism or whatever the medium is, right? So this right here is our critical angle, and that's for 1 mark. They want us to identify that, and then we are good, right? So that's all for 15 marks. And again, this was from the January 2023 paper. We haven't done June as yet. So this is from January 2023. And again, this is just a question on wave motion, refraction and reflection of light, refractive index, and all that stuff, that good stuff, right? So again, make sure that you understand everything here. If you don't, drop a comment and let me know. I'll be happy to clarify anything for you, okay? All right, I'll see you in the next video.